Okay, so today we will talk about predicting redox reaction, which in our plan for the start of electrochem is point 4. So up to now, what we have done is we have seen all the introduction to chemistry, oxidation and reduction, writing half reaction equations, and on this we had another video which was dealing with the oxidation number and the rules so that we will apply. For today, or for now, we will focus on the predicting redox reactions. And just bear in mind that this is a bit of a long video, but bear with me because up to the end of this video, you should be able to predict any redox reaction, no matter what is the situation that you will face. At the very first video that we had when we presented the introduction to the electrochemistry, we talked about the spontaneous reactions and non-spontaneous reaction. And spontaneous reactions were reactions in which the electrons were freely were able to move from one metal to the other, compound to the other, and on that way they were producing electricity, because remember what we said in terms of the electrochemistry. So I don't want to go too long on that. However, it is a very it is hard to remember all of the reactions possible that we have in our world, and then predict and say that this is a spontaneous and this is a non-spontaneous reaction. So in this case, let's say element A is willing to give the electrons to element B, or element B is willing to accept the electrons, and so on. To help us, we have, through the experiments, there is a table in your page 7 of your data booklet in which easily identify if the reaction is a spontaneous reaction or is a non-spontaneous reaction. Happens naturally or doesn't happen naturally. The page 7 in your data booklet look exactly like this one here. I just copy and paste it here in my video. So now let's identify if two given reactions are spontaneous or non-spontaneous. So let's suppose that we have magnesium 2+ is reacting with potassium, and let's identify if it is a spontaneous or non-spontaneous reaction. And then on the other hand, let's take a look at magnesium 2+ and tin. Is it spontaneous or non-spontaneous reaction? So let's talk a bit about this table here that you see in your data booklet on page 7. When you see this, you'll have two sides. The title of the table first is a reduction half reaction. So when you see this table, you'll have two sides of the reaction, which they go in both ways. So you can write, let's say, fluorine 2. I will use a different pen. Fluorine 2 gas, which is the very first one here. The very first one here. Plus 2 electron has 2 R's like this, is 2F -1 aqueous solution. So when you see this, you can write it in both sides. You can write it from going from this direction, or you can write it going from this direction. Keep in mind, what do we have? That one of them is when we are writing a half reaction, half oxidation, and half reaction oxidation, and the other one is half reaction reduction. Remember what we said about the oil rig or Leo the lion gets do or whatever girl. So oil the rig is that the oxidation is a losing, and reduction is gaining. And then we said that whatever is oxidizing is becoming an reduction agent, and whatever is gaining is becoming oxidation agent, because agent means that you are serving as a way to be either oxidized or reduced. So when we see this table, that we see that, let's suppose fluorine is gaining 2 electrons, this is becoming a reduction reaction when we see it from the left to the right of the reaction. But actually, in terms of the agent, those are the oxidation agent. So this table is sort, and write this in your data table as well. This table is sort as the oxidation agent going from the top being the strongest oxidation agent from the strongest to the weakest, and for the reduction agent, it goes from the top up, sorry, from the bottom up to the top, reduction agent, the top being the weakest and the bottom being the strongest. Okay, so oxidation agent are on the left of your data table, and reduction agent are on the right of your page 7 on data book. So now what I do, there are several methods, but I will present to you the first one, which is very visual one, and I will erase this so that we have more, we see it better. So the way that I see it is that I identify which one is like oxidation agent and which one is a reacting agent into the reaction, and then I see if the imagine now that you have the electrons in your hands and you are dropping them. Do they naturally go to the element or whatever your compound that you are looking for? If it does, then it's a spontaneous reaction. But if you have to push them up, then it's a non-spontaneous reaction. So now let's see here, and I will leave it, I will suggest you to stop and identify which one is oxidation agent and which one is reducing agent in the first equation that we have, magnesium 2 plus with potassium. So you should have that magnesium is the oxidation, magnesium 2 plus is the oxidation agent, and potassium is the reducing agent. So now let's take a look at this magnesium and potassium that we have here. So magnesium 2 plus is somewhere in here, and potassium is somewhere in here. So now imagine yourself that you are standing at magnesium 2 plus and then you are dropping 2 electrons. Do they naturally go to the to potassium? Yes. Another way that you can see it is if you have an arrow that goes like this, or some teachers do the waterfall. So does the waterfall naturally to the lower position? Yes. So we can say that this is a spontaneous reaction. It happens without the need of any battery into it. Now let's take a look at what is happening with magnesium 2 plus and SN. Magnesium 2 plus again is the oxidation agent, and tin is the reducing agent. So when we take a look at it, SN or tin is somewhere in here. So if you are standing at magnesium 2 plus and you want to drop the electrons to tin, you can't, because it is that you have to go up to reach the tin. So this is telling us that this reaction is a non-spontaneous. So the first method to identify if it is a spontaneous or non-spontaneous when you have a reaction is just by looking at the oxidation agent and reducing agent and see if the fall is natural or it needs a push. If it needs a push, is non-spontaneous. If it is natural, then is spontaneous reaction. Make sense? So this being the first method, just by looking at the table and drawing the line, method 1. The second method is by taking a look at the electric potential of the compounds, or whatever, electric potential of the compound. So when we see magnesium 2 plus has an electric potential of negative 237, and when we see potassium has an electric potential of negative 2.93. But the reaction will be something like this. So when we have magnesium 2 plus, as you see even in the reaction here, plus 2 electron will give us magnesium solid, and then potassium, this is what we have here, and we have 2 potassium plus 2 electrons, because everything is multiplied by 2, but potassium and 2 electrons, and we can write it as a reaction like without the 2, will give us potassium, will be a potassium ion plus 1 electron. So when we take a look at the electric potential of magnesium 2 plus, will be negative 2.37 volts. And since we flip the equation on this, on the potassium one, then we will flip the sign of it. So will be positive 2.93. And when you add those two together, will be a positive value. And since it is a positive value, that means that you have a spontaneous reaction. So 2.93, 2.37 equals. So this will be positive 0.56. That means that magnesium is willing to take more electrons into its structure. And when you take a look at the other one, the magnesium and tin, then the half reduction reaction will be something like this. Magnesium 2 plus 2 electron is a magnesium solid, and we will have an electric potential of still negative 2.37. And when we flip this in the other side, then we have tin. Tin will be tin 2 plus 2 electrons, and flipping the sign as well will be negative 0.14. When you add positive 0.14, because it's negative, the other side will be positive. When you add those two together, you will have a negative value, which means it is non-spontaneous. So if this is spontaneous, the other one is non-spontaneous. And the value on this case will be negative 2.34 minus 0.14 plus. So it's negative 2.23. So when the difference of potential, electric potential energy is negative, then it is a non-spontaneous, meaning that the electrons are not willing to go, but you have to push it with something else. Okay, so those are the first way, that is the visual one, the first type of questions that you will see in predicting the spontaneity of the reaction. Is it spontaneous or it is not? And you'll have two ways to do that. The first one is just by looking at the table and seeing if the fall is natural. You may assume it as it is water that is falling or electrons that are dropped. If the drop is natural, then it's spontaneous. If the ridge to the other one is from oxidation agent to reduction agent is a jump, then is a non-spontaneous. Or you can take a look at the voltage, electric potential, and then if the difference of the two is positive, then it's spontaneous, and if the between the two is negative, then it is a non-spontaneous reaction. Now we will move to more complicated questions when we have words, and I will list you the steps that we have to do for that.